In this problem, I'm going to be taking a cantilever beam and apply to it a sudden load, okay, load of 100 pounds suddenly applied at the tip. Now, we can do this thing as a transient dynamics problem, which means in the context of Catia, it's going to be modal superposition or transient dynamics or linear dynamics, basically. These are all the same thing. And I'm going to be using beam elements. And as far as the modulation goes, I'm going to use the white noise modulation instead of me giving Excel spreadsheet, which says at all times the magnitude of the load is 1, essentially becoming a dynamic problem. I'm going to say it's a white noise, and that means exactly the same thing. In other words, the value of the load for all time is the same thing. For example, 1 times this 100 pounds, and it's going to make it a dynamic problem, by the way. The data that I'm taking is from the previous two tutorials on transient dynamics. One of them was a harmonically applied load at some point, but it was a simply supported beam, of course. And then I repeated that using solid elements, but here I'm going to use beam elements. Okay, so let's go ahead and do this. We will define 3 points, one for one end of the beam, which is the wall, basically. Then the other end of the beam, which is the free end. Okay, and finally, because the cross section is a rectangle or a square, I need an orientation point. So I'm going to choose any point which is off this line. For example, I can choose maybe x of 5 and y of 0. This point is going to be used as the orientation point. Now, we're going to need a line going from this point to that point. Okay, and apply material to it. The properties that are given in that slide is properties of steel. So metal, steel on that part. Say okay. And that's pretty much it. So we're going to go to generative structure analysis. Because the load is applied at the tip, I don't have to do any fancy things like the simply supported example that I did. The load was applied actually at 1/4 of the distance. So I went to the advanced meshing tool, created a point here, made sure that that point is actually a node. But we don't have to do that here. Okay, so let's go ahead and mesh it with beam elements, nothing fancy. How about making one element along the length? So, I mean, 1 inch long element, so that's 20 of them here. All right, and then the properties is going to be rectangular, support is there, rectangular, size is 1 and 1. These are from the previous problem that we did. An orientation point, we're going to use this, which slightly tilt this thing so that it's in the orientation that we want. Just look like that. Okay. Now, I'm going to hide these points. One end is clamped, so that is this end is clamped. Okay. And because I want to do a transverse vibration here, let me take all of these points, all of this entire line, say does not move in the direction x. Does not move in the direction x. This basically takes any out of plane motion and will prevent that. Nothing will move out of the YZ plane. Okay, good. Now, we're going to apply a load here. This is a static load right now, so we're going to apply a static load of 100 pounds downward to this location. And you can see that it's right here. This is the load that we applied. And there's nothing fancy. If I just run this thing, it's going to bend down. I mean, this is an obvious static problem. Incidentally, you know what the maximum deflection is going to be FL cubed over 3EI. That's the standard formula that you know from strength of material. But anyway, so if I change the rendering here, you can see it better probably. Yeah, right there. Maximum deflection at the tip. Now, because we're going to be solving this is a dynamic problem, so this load is applied instantaneously. That means that this becomes a dynamic problem, and I'm going to use the modal superposition or transient dynamics. I need to extract frequencies, natural frequencies of this. Okay, so let's go ahead and insert a frequency case. And we use for the restraints the reference from the static that we use right there. We uses these restraints, which was basically cantilever. It does not move in that direction. And that's pretty much it. If I run this thing, it's going to extract 10 frequencies, the first 10 natural frequencies. Okay, so if you look at the deflection, and if you click on it, these are the frequencies that it extracted. Okay, these are all. Yeah, you can see that they're all in plane bending frequency. There may be some axial ones too. This one is axial for sure. This is axial. This is again bending. All right, so that's fine. You just leave it the way it is. And let me deactivate this plot. Okay, so now we're going to insert a transient dynamics. It says, okay, what is the frequencies that you extracted? In other words, where are they? Right there, right there. Okay, and it's a load excitation. That's fine. Okay, so the only thing is that our modulation, notice that you can give it a spreadsheet, Excel spreadsheet, or we can say white noise. White noise means that it's as if you have two columns of the spreadsheet. One of them goes different time. Column one is going to be time. Column two is going to be amplitude of the load, and it's going to be constant, obviously. Okay. Instead of doing that, I can say there is the white noise, and it's just going to create it, and it's right there. You can see that the white noise was created right there. Okay. And now we're going to say, okay, so if you expand this thing, the load excitation, double click on it. It says, what is the load? The load is what we applied in the static case, which was right here. That was the concentrated force, downward 100. And the modulation is just this white noise modulation. Okay, let's see under how much time do you want to excite this thing? So let's say that you want to do this thing. For now, let's make it over maybe 1 second. And let's do 100 steps. These are not random numbers that I'm putting in there. Obviously, for that natural frequency will impact whether the problem is static or dynamic. Okay, so usually because you can't apply things instantaneously, you have to ramp it up, and if you ramp it up very quickly, in other words, if that duration that the curve is ramping up is much smaller than natural period of the oscillation, the first natural period is going to be the dynamic problem. Okay, but anyway, we will find out. So that's pretty much it. So we don't have to run anything. We just have to go and let's look at the deflection of this tip. How about that? Deflection of the tip. In the problem that I did with simply supported beam, I created a point here, or I monitored the deflection of the middle point. Okay, here we're going to monitor the deflection of the tip. So right click, generate 2D plot, and then finish. Then it says, okay, go and select your node. Let me hide cross section. Okay, so let's say we look at this. This is a midpoint, say something like that, almost a midpoint, and we say okay, close, and then we can double click on it, and it shows you the oscillation. Now, let's check a few things here. First of all, the duration was 1 second. Now notice that this is very jagged. That means that you should be using more more integration. No, it's not integration point, but more. Let me see what the naming for this steps, not more steps. So let's try 1,000. See what happens. Double click on it. Oh, sorry, double click on the results. Now you can see that it's not as jagged as we want. Now, why is there a damping here? Because if you go back there, you'll see that if you click on the damping, by the default, it takes 1% damping. So if I want no damping, 0, oops, 0, and say OK. All right, and now double click on this. You see that the damping is gone, basically. And in the event that I go there, and change the damping, let's say, let's make it, how about 50% damping, highly damped, okay? So run it. Don't run it, actually. Double click on this thing. It's going to take, yeah, you can see that it's so damped. Look at what happened. It immediately dies down, okay? Yeah, so that's pretty much it. So white noise is basically when the load is instantaneously applied, so you're dealing with a dynamic problem, and that's pretty much it. Good luck.